and screen share. Okay, are there any questions before I start? Okay, so as I said, um, sometimes first order conditions describe a minimum rather than a maximum, right? So that's one potential pitfall or trap that you have to be aware of. Um, so that means that at the point of tangency, if you have an integer solution, you have to make sure that the indifference curves are convex at that point, right? Uh, if they're convex globally, if the convexity axiom is true in general, then the second order conditions will always be satisfied. Um, how do you check in general whether in a constraint maximization problem, whether second order conditions hold or not at the point of optimum, meaning at the point where the first order conditions are true? Um, so this is the general formula. I won't spend too much time on it or try to derive it. Again, it's a matrix-based condition. In maths, you will cover these in more detail and probably see proofs and all. But again, just as a recipe book approach, this is what it takes. Suppose we are solving this problem: maximize an objective function f of x, subject to a constraint g of x equals 0. Uh, to check the second order conditions, you um, construct this matrix. So in this matrix, except for the first row and the first column, everything inside is a second derivative of the Lagrangian function, right? Stacked up, written in this form. And the rows and the columns are the first derivatives of the constraint function, the gx function. And you have to make sure that the principal minors of this matrix alternate in sign, starting with positive. Yes. Um, so I'll just state that and move on, and you can show that if we have a strictly quasi-concave utility function, then this will hold everywhere, not just at the optimum point. Um, the okay. Uh, Let me get to two mathematical results which are very important, which are used extensively. So I want you to understand them. First of all, what they state, some idea of why they're true, and lastly, how they're used. Give you some indication to that effect. Um, Okay, so the two results that we will be talking about are the implicit function theorem and the uh, envelope theorem. Okay, so first, let's get some terminology in place. Um, suppose we're solving a problem like this. Maximize a function. Two vectors. X is the vector of choices. These are the variables which are endogenous in this problem, right? Maybe these are the variables that will be chosen to optimize the function. That's the vector X. What is A? A is a vector of given parameters or exogenous variables. They're given from outside, right? You can't freely choose them to maximize this function. Subject to some sort of feasibility constraint that X cannot be anything, right? It has to come from a certain set. In the consumer's problem, that set was the budget set, right? All bundles, all vectors, whose cost did not exceed the income of the consumer. Uh, so a general way of describing a constraint is in this form, right? That X has to come from within a set. That set could be described by a set of equalities, inequalities, what have you. I have made the set itself, or the size or the shape of the set, a function of the parameters. Okay. Uh, so it's a function of vector A. So if any one of the parameters change, then both the feasible set will potentially change. And
newspaper ले आइयो बाबू.
Yogesh, please turn off your mic. Thank you. So when a parameter changes, it also may change the shape of the objective function, right? We are being abstract, but you'll see the connection to the concrete economic problems that we are interested in very soon, okay? So bear with me with the abstraction just for a little while. Okay. Now, why are we sort of setting up this apparatus? Well, we are often interested in comparative statics exercises. I've used the term before, and but just to make sure everybody is on board. What are comparative statics exercises? These are exercises where we are interested in how an economic system or a set of economic choices change when some external parameter changes, right? So if there's a recession and consumers' incomes go down, how does it affect demand functions, market demand? How does it shift market prices and volumes of trade, and so on? Yes. So many interesting economic questions are of that form, right? If there's a price shock in the crude oil market, right? If suddenly, the OPEC increases crude oil prices, we are often interested in, how will it impact the transportation sector, the agricultural sector, the economy as a whole. So again, that's a comparative statics exercise. The crude price is a parameter which has changed. Guys, please keep your microphones off. Keep in mute mode unless you want to ask a question. Right? So almost any kind of interesting economic question takes that sort of form of a comparative statics exercise, and we are trying to set up a set of powerful tools to handle comparative statics exercises. Okay, now, so we have to, again, remember terminology. F is the objective function, and this is the constraint set. Now, let me define two terms: a choice function and a value function. Okay, what is a choice function? A choice function is essentially the optimal values of X as a function of the parameters, right? Fix the values of the parameters, you get a certain optimum vector X star, which will solve this problem. Change around the value of the parameter, pick a different parameter, pick different vector, you will get a different set of optimal choices. Pick a third set of parameters, you'll get a third set of optimal choices in terms of X. So construct this whole mapping, and that is what we call the choice function. Yes. In the consumer's problem, what are the parameters?
Sir, income.
Income and prices, right? And you may have parameters from the utility function. If you have a Cobb-Douglas utility function, it will have exponents on x to the power alpha, y to the power 1 minus alpha. So those alphas will also be parameters of the problem, right? Those are kind of taste parameters, the relative liking of one good over other. So what are the endogenous variables? What are the X's in the consumer's problem? It's the set of quantities that the consumer finds optimum to buy, right? Or the demand functions. Yes. So the demand functions are the choice functions in the consumer's problem, right? and they're functions of prices, income, taste parameters, and so on. Everyone with me? Okay, choice function is a general term for any applicable to any problem, right? In the consumer specific problem, the choice function is called the demand function. Now, the value function, what is the value function? The value function is the optimized value of the objective function. Once we have chosen and found the optimal values of x and plot that into the function, and we have pushed the function to the maximum that it will go, that is what the value function is. Again, the value function is the optimized value of the function as a function of the parameters of the problem, right? So v as a function of a. So keep an eye on the question, function of what? Function of the parameters, right? So you can describe it in two possible ways. It's just the maximized value of the function subject to the constraint. Another way, an equivalent way of describing it is that you go to the objective function and you plug in the choice function inside the objective function. That gives you the value function. Okay?
Excuse me, sir.
Yes.
So can you please explain this expression x star into a is equal to arg max of f x?
I'm sorry. If you haven't seen this before, max of f of this means the maximum value of the function, right? Argmax means whatever value of x maximizes the function, that is what we are referring to. Yes. Arg is short from argument. X is the argument of the function. X is the variable which is sitting inside the function. It is a function of x, right? So what is the value of x which will maximize the function subject to constraints, etc.? That is what is called argmax. So the distinction between max and argmax is that argmax is what is inside that will give us the optimum, and max is the optimum value of the function itself. Is that clear?
All right.
Yeah. I thought you guys were familiar with the argmax, the meaning of argmax. So always stop and ask for clarification when I assume something which I shouldn't. All
Sir,
right.
can you explain once again this difference between choice and value function? It isn't very clear.
Okay, so let me use as illustration. So let's look at the consumer's problem.
Sir,
Yes.
so whenever we are concerned about the variable inside the function, do we write arg before it? Like that is the significance of arg.
Let me just. Okay, let's take a concrete example. All right. So our consumer has Cobb-Douglas utility function. So let's illustrate these concepts with that problem. Okay. Sorry, just give me a minute. It's the writing pad is not registering. What's the matter? This is awful. Let me see if I can restart it. Hmm. That's awful, guys. I somehow my writing pad has stopped cooperating. I have no idea what the problem is. Ah, well, I will need it. Just give me a couple of minutes, right? I have another one, and let me see if that works. Otherwise, we'll have to try something else. Just a second.
Sir, we can discuss this later to Agar, if it's taking a lot of time.
It is taking a lot of time, but I will need this for other things. That's why I'm persisting a little bit, but I don't know what the problem is. I've tried a different port. Oh God. All right, so just let me for now move on. Okay, so let's think of the consumer's problem, right? And try to make these concepts concrete with the help of that. So in the consumer's problem, what's the objective function?
Utility.
Utility function.
It's the utility function, right?
Utility.
What's the feasible set? It's the budget set, right? It's the budget line and everything under it. Okay. What are the choice functions? The choice functions are basically the demand functions. Take any vector of parameters, namely prices and income and taste parameters. Well, fix the taste parameters. For any vector of these parameters, the consumer solves utility maximization. That gives you the optimum quantities of each good. And so you can express those optimal quantities as functions of prices and income. That's what we call the demand function. Yes, the choice function is the generalization of the demand function, right? It's the same idea, the same kind of thing for an arbitrary problem, right? Not necessarily the consumer's problem, but any constraint optimization problem, right? So the demand functions are manifestations of the choice function in the case of the consumer's problem, right? It is those values of the choices which will solve our maximization exercise. for each set of parameters, for each vector A. Okay, that's the choice function. Right? So in the consumer's problem, the demand functions are choice functions. Choice function is the more general concept. Demand function is the choice function of the consumer's problem. All right. Now, what is a value function? Once you've found the choice function, once you've found the demand function, for example, in the consumer's problem, you can plug it back into the utility function, and then you get what is called the indirect utility function, right? The direct utility function is the original utility function which the consumer is trying to maximize. That utility function is a function of quantities, right? In more general form, that is a function of the x's and the parameters potentially. Now, once you have found the optimum x vector, once you have found that and you have plugged it back, right? So in the consumer's case, once you have found the demand functions, if you put it back into the utility functions, what are the demand functions? A function of prices and income. So when you plug it back into the utility function, you can express utility as a function not of quantities, but of prices and income, namely the parameters. Yes. So that is called the indirect utility function, and it is a specific instance of a value function. Value function is the more general concept. Yes. So to sum up, choice function is that vector x which solves the maximization problem. Value function is what you get after plugging in the optimum vector x into your objective function.
Sir,
Yes.
sir, what is the intuition behind value function? As in, like, if we have already got a choice function of x, why do we actually need the value function? Why do you actually need to, get utility in terms of prices and incomes?
Okay. First of all, I mean, uh, I'm always free to define it, right? Let's say freedom of speech allows me to, even if it's useless, I can always say, oh, this, I'll call this the value function, right? But fair question. I don't mean to be dismissive about the question. Absolutely. Why are we, spending time developing these concepts? You will see. You will see very soon. Okay. For example, when you do macroeconomics and you do problems which involve many time periods, right? Intertemporal problems. There's an optimization technique there called dynamic programming, right? And value functions play a very big role, right? For example, when you try to decide how much of your income to save today, right? Whatever you save, you carry forward to next year, right? And then you have to decide again how much of that you want to save for 2 years down the road or 3 years down the road. Yes. So the value function there comes in very useful because you ask yourself, okay, if I save 20% of my salary this year and carry it in the future, what can I do with that, right? Well, you'll have to think ahead and you'll have to think of, what's the optimum way of spending that 20% which I save and carry forward. And once you do that, you plug that in and you find the value function of this 20% savings that you're carrying into your future, right? Whether it's worth saving that 20% depends on what is the best use you can make of that savings in the future. Yes. And for that, you need to know the value function. So that's just an instance, right? But you'll very soon see. I mean, you have to be a little patient. There's a reason why we're developing these concepts, and they'll come in sooner rather than later.
Thank you, sir.
Sir, one more question.
Right. Go ahead. Go ahead.
Sir,
Yeah.
so we are saying that A is a set of exogenous variables,
Yes.
while X. So can you hear me? Yeah. So I was saying that X is a vector of exogenous variables, while X is a vector of endogenous variables. So why we are
Sorry, you're
the
cutting off
set
a
of
little. You got a little bit cut off. I don't even see who's asking the question.
this Asta.
Okay, can you repeat the question, please?
Yes, sir. Sir, I was saying
Palak, there's huge audio problems. Sorry.
Sir, I have not question.
Oh, okay. I don't know who's asking. Anyway, I'll move.
Sir,
Yes, Hemant.
so a value function is basically function of the choice function and the parameter. So, sir, can't we say that value function is the same as indirect utility function?
Yes, it's the same. I mean, the difference is that the value function is a general concept, right?
And indirect utility function is just limited to
Yeah,
the utility function.
right, right.
Okay, sir.
sorry, sir, little connectivity issues. So I was saying कि we are defining A as a set of exogenous variables,
Yes,
while X is a vector of endogenous variables.
right.
So, sir, in by A we are capturing price and income, while through X we are capturing quantities. Then in the first line we are saying that X belongs to the set of A. Like why we are saying that X belongs to set of A while X is completely different from.
No, X doesn't belong to the set of A. X belongs to a set of X's, right? X has to be drawn from a set of X's. That set is dependent. That set changes if any of the parameters change. So again, think of the consumer's problem, right? In the consumer's problem, the set A, right, is the budget set. The budget set, each element of the budget set is a quantity vector. It's not a vector of prices, each element. But the boundary of the budget set depends on prices. So A is an argument of this set function, if you will. Right? So that's
Okay,
exactly
sir.
the analogy. Every element of the budget set is a quantity vector, but the shape and size of the budget set is a function of prices.
Okay, sir.
Yeah. All right. Now, let me get to the implicit function theorem. Now, why do we care about this theorem? Here's the thing. Most economic models essentially boil down to a system of equations, right? In the consumer's problem, what is the system of equations? Anyone?
Budget constants.
The budget.
Budget constraints.
No.
First order derivative, Lagrangian function.
It's the first order condition.
Second derivative.
It's the first order conditions, right? For interior solutions, they're described by the first order conditions. Remember, all the first derivatives of the Lagrangian equal to 0. That gives you a set of equations. And that's the equations, those, when you solve that set of equations, that gives you what you're looking for, your demand functions. So the heart of the model is that set of equations. Yes. In a market, what is the relevant set of equations?
Demand and supply equations.
That's right. Demand equals supply, right? If you're looking partial equilibrium, one market, you get one equation. If you are doing general equilibrium, several markets simultaneously in equilibrium, then there will be a market clearance condition for each. So that'll give you a set of equations. So many models and analysis boil down to a set of equations. Now, when your model is a set of equations, and you are interested in some sort of comparative statics. When a price goes up or when income falls, how do the demands of various commodities, how do they respond, right? That's the kind of question. Now, you might say, what's the big deal? I'll just go to my set of equations, I'll explicitly solve them, right? I'll write down the solution. And then if you ask me, right, so I'll explicitly find my demand functions. Okay, you give me a Cobb-Douglas utility, like in an exam problem, I will derive my demand functions. And then if you ask the question, you know, what happens when price goes up? How does the consumer respond? What is the elasticity, etc.? I can just look at the solution and answer that. Here's the issue. In an exam, we give you an utility function, right? But when we are doing a general analysis, we often don't know what the utility function is, okay? And we don't want to assume a specific functional form. We can ask a question that in general, what happens if prices go up or incomes go down, et cetera, for very general utility functions, right? So we may not specify what the exact form of the utility function is, but still we may want to answer some comparative statics questions. In that case, when we don't have explicit solutions, how do we, is there any way, any hope at all to derive comparative statics results, right? And that's where the implicit function theorem comes in. That yes, we can take a detour, we can, without doing the explicit solution, we can have a workaround where we can say specific statements about comparative statics without solving it explicitly. How do we do that? That's where the implicit function theorem plays its role. So here's what it says. Consider a set of, now we'll zoom away a bit and go abstract, and then I'll maybe make it more concrete with examples. Consider a system of n continuously differentiable equations, right? So we have some model which gives us a system of equations, which is, you know, in the most compact form, we have written this way, right? X is a vector of variables, A is a vector of parameters as before. F superscript I is the ith equation in our system of equations, right? And since if we have n variables, we'll need at least n such equations, right? So this is a system of n equations. I goes from 1 to n. Two questions. One is, when does a solution exist? Okay. Sometimes a system of equations may not have a real valid solution. So one worry is a solution may not exist. And the second is, how do we do comparative statics if we don't even know the explicit form of these functions, or we have not been able to solve them explicitly, maybe, yeah, because it's sort of too complicated. So a very important construction is the Jacobian matrix. So that's what I've written down here. What is a Jacobian matrix? It's the matrix of all the first partial derivatives of our functions, right? So the first row is all the first partial derivatives of the first function coming from the first equation. The second is for the second function coming from the second equation, all the partial derivatives of that, and so on down to the nth function. Okay, so this is the Jacobian matrix. So when does a solution exist? Solution exists when the determinant of the Jacobian matrix is non-zero. Okay, so that if you calculate the determinant and find non-zero, then that is that. And you'll see in a moment why we need that. So then there exist explicit solutions, which are continuous, differentiable, well-behaved, and so on, of this form. More importantly, now here the notation is a little bit dense. Is there any way for us, as I said, you know, how to determine or analyze how these x stars, this vector, right? What is x star? X star is the solution. Okay, it's not an arbitrary x vector. It's that x which solves this set of equations. And obviously, although it's not written here, implicitly what we mean is that this x star will be a function of the vector A. the vector of parameters. So how does this x star change if some parameter, let's say the kth parameter, a of k, changes, right? Can we characterize that? Well, that the implicit function theorem says that this is how, okay, it's the solution is basically this partial derivative, right? How the ith endogenous variable changes in response to a change in the kth parameter. That's what this derivative is, right? It's given by this formula. In the denominator, you have the determinant of the Jacobian matrix, and that's where this comes in, right? If this determinant was 0, then this would be just undefined. This has to be non-zero. And what is J of k? J of k is basically the Jacobian matrix where the kth column has been replaced by the vector of partial derivatives of the function with respect to the functions with respect to the kth parameter, right? So del f1 del ak, that's the first element of that vector. Del f2 del ak, that's the second element, and so on. So you have a vector of these partial derivatives of the function with respect to the parameter that we are interested in, right? So you take the Jacobian matrix, replace its replace its ith column, right? We are interested in dxi dak. So replace the ith column of the Jacobian matrix by that vector of partial derivatives of the parameters. I'm sorry, this is exactly where I needed to write something, but this has broken down, so I'll have to fix it. Right, I can show it's quite easy where this formula comes from, right? So if I write it down, I can show you, where this is coming from. For now, let me not try to fix this again. Maybe later, if you ask me, I can show you where this is coming from, right? But the bottom line is, this is a powerful general technique of doing comparative statics exercises, deriving comparative statics results without explicitly solving the set of equations that describe that particular model, right? In your, I have given one or two, in the first problem set, for example, there's a total non-economics problem which I gave you, right? The cricket problem, if you remember. Yes? So in all of those problems, we can apply this sort of powerful reasoning technique, and we can say something about the question, right? That in the cricket problem, the question was, if the Indian team is playing a stronger bowling attack, should it take more batsmen in the team or more bowlers? Right? Classic comparative statics question. So we can use these techniques to answer questions in many contexts, not necessarily markets and prices. Questions?
So in the beginning of this topic itself, you told us like we'll use this technique when we don't know the utility function. But even to find the determinant of the Jacobian, we would require the utility function and hence the first derivatives.
Yes. So so go back to your, I don't know if you guys remember the cricket problem. I think the TAs discussed them in the tutorials. Discussed that problem in the tutorials, did they?
Yes, sir.
Yes.
Okay. So I'll trust that it's somewhat lodged in your memory, if not firmly lodged. So in the cricket problem, through comparative statics techniques, you calculated a derivative, right? The optimum number of batsmen as a function of
Bowling strength.
bowling strength of the opponent, right? D batsman, D bowling strength, basically, that derivative, right? And that derivative if you remember, the expression involved partial derivatives of the various functions, right? Those functions, we didn't assume any functional form. We just said, okay, this derivative we are interested in, optimal number of batsmen, how it responds to bowling strength. It's the ratio of these partial derivatives of our objective functions, etc., etc. Yeah. And then if we, to put a sign on that derivative, is it positive, is it negative, right? Should we take more batsmen or less batsmen? Basically, it depends on the signs of those partial derivatives. So yes, we are not taking a specific functional form of the utility function, but we have made some assumptions about the utility function. For example, all the first derivatives are zero, all the marginal utilities are positive, and the function is quasi-concave, which tells us something about second derivatives, right? So often we can use those to look at our comparative statistics, to look at something like this that we have derived, and assign a sign to it. We can say something qualitative that, you know, this will be positive, this will be negative. And it comes from assumptions, general assumptions about the shape of the utility function. Again, we'll see sort of illustrations of all this as we go along. Yes. So yes, so it's not like, you know, we are sitting somewhere in the middle. We haven't specified exactly what the utility function is, but we still have narrowed down the possibilities by making some assumptions about the shape, about first derivatives, about second derivatives, and that information often is useful. Yes.
So
yeah.
So where did we get this equation from, this J dx star is equal to df? Like, what does that like? What does that mean basically?
You know, it is for this slide, I needed to really write it down. I mean, this notation is very opaque. Let me not try to answer it right now. Okay. Let me skip this part. Just tell you what the result is, what the implicit function is here, saying. I'll try to clarify this once I fix my whiteboard. Yeah. Okay. So please bear with me. Yeah.
So just one more doubt.
Yes.
In JK, we say that we are going to replace the ith column with the.
I really should. This is a little bit of. I should have said J subscript I, right? So it's really a typo. So we replace the ith column with this vector. Look at this vector.
Yes, sir.
Yes, you replace the ith column by this vector.
Okay, okay, sir.
Okay, let me move to the envelope theorem. Guys, switch off. Put yourselves on mute. Mute yourselves, please. Unless you ask a question. Okay, thank you.
Sir, yes. This Jacobian matrix method is used only for optimization problems or any system of equations?
No, any model, any problem which boils down to a system of equations. Yes. The example I gave, which is not coming from optimization, is a general equilibrium market clearance model. You have a set of markets. In each market, demand has to equal supply. So that gives you one equation from each market. And so you have n markets and n market clearance conditions, one from each market. That's a system of equations. And we can do comparative statics on that.
Okay, so thank you.
Okay, so the envelope theorem. Yeah. So we have a value function, which is this, which is basically the outcome of this maximization. So the Lagrangian is this, right? Objective function fx plus multiplier times the constraint function. You can have more than one constraint. Now, often we are interested in the question. So here, often we are interested in the question, how does a value function shift when the kth parameter changes, right? The slope of the value function with respect to the parameters, right? So in the consumer's problem, you can say, okay, what is the slope of the demand function with respect to the price of some good? Yes. But you can also ask, what is the slope of the indirect utility function as a function of these prices? Okay. So here's what the envelope theorem says, that the slope of the value function with respect to kth parameter is nothing but the slope of the Lagrangian function with respect to that. So if you want to calculate the slope of the value function, just go and take the corresponding derivative of the Lagrangian function and you're done.
Please mute.
Please put it on mute. Topolina, please mute yourself. Switch off your mic. Okay. Right now, okay, I've stated it sounds like a damn squib, right? Or what's the big deal? What does it mean, etc. Let me clarify and explain. Let me go to the simplest form of these optimization problems and try to give you the intuition and then back up from there. So what is the simplest optimization problem? This is the simplest optimization problem. One endogenous variable, one parameter, you're maximizing the function, zero constraints, right? So as simple as it gets, it cannot get any simpler. Unconstrained optimization, one variable, one parameter. Let's think of that problem, okay? Let's kind of make it real life. What is this? This is, let's say, X is the amount of irrigation water a farmer puts on his land, right? Applies to his land. A is the amount of rainfall, right? Rainfall chosen by God. We don't choose it, but we can choose how much to supplement rainwater with underground water, irrigation water supplied to the field. Okay. And what is this function? The function is, let's say crop yield. Okay, so we are trying to maximize crop yield on the farm, or the farmer is. All right. So what is V of A? V of A is the optimal yield function, right? If everything were chosen optimally, if irrigation water was chosen optimally, then this would be the yield as a function of rainfall, right? So if you can derive this function, you can tell what the yield will be in drought years, in flood years, in normal years, after taking into account how the farmer optimally responds to it. Yes. And what is XA? XA is the choice function of the problem. It is the optimum amount of irrigation water to apply as a function of rainfall. Yes. Okay. So we'll have a first order condition, again, assuming interior solution, that the partial derivative of our yield function with respect to X, right? The choice variable should be equal to 0. And if I plug in the choice function in this equation, then it becomes an identity just as before, right? This is basically what the implicit function theorem, the trick which it does, right? Once you plug it in, it's an identity, you can equate the derivative, etc. So,
Sir,
yes.
you have put x is a function of a in the first order condition, not in the simple problem like the maximization function.
Yes, I have plugged it into the first order condition. Absolutely. Right?
Okay,
First, I first wrote down the first order condition. It was an equation. And then when I plug in the choice function, then it becomes an identity. Right? Every time A changes, the choice function itself kind of changes. Right? And it changes in a way to guarantee that the value still is 0.
Okay, sir.
Right? So for every value of the parameter A, rainfall, this equality is maintained. So it's an identity, and that's the reason we can equate the derivatives of two sides. Yes. In the implicit function theorem, sorry, it's, the breakdown of this board is the kind of proof that I skipped. In the proof, exactly this trick is utilized, right? Everything is an identity, so we can differentiate and equate the derivatives of the two sides. So in that, very abstract ji divided by j, all of that, when you try to prove it, you're just extending this reasoning, which is centering on, okay, this is an identity, so I can equate derivatives. Okay, so let's differentiate and equate it. So differentiate both sides with respect to x. The right hand side is just 0, right? It's a constant. On the left hand side, you'll get this, right? Applying chain rule and all. Okay, first from the first part. I'm sorry. Differentiate with respect to a, the parameter. Yes. So this is pretty simple, right? There will be two terms, because a, first of all, directly affects the function. So that's captured in f of xa, this cross partial derivative. Moreover, a affects the choice function, and through that affects the function. So this is the, coming from that. So you can think of this as the direct effect of change in a, right? And this is the indirect effect. So that is equal to 0, and that allows us to solve for x prime of a. So this is how the choice irrigation responds to rainfall. That's given by these partial derivatives. And the question that somebody just asked a moment ago, right? If we don't assume functional forms, how do we still say anything at all from our comparative statics? Well, here's the illustration. We may not assume a functional form, but we, for other reasons, for economic reasons, for empirical reasons, we may put certain signs to these partial derivatives of our primitive functions. Yes, we may want to say, so what is this? This is f of xa. This is the interaction between irrigation water and rainwater, right? For example, you may want to say, they are substitutes. So that means if there's a lot of rainfall, then the marginal benefit of irrigation water is less. So maybe this is negative. Okay. You might say, okay, this is also negative because there's diminishing returns to irrigation, right? As you apply more and more irrigation water, its marginal value gets less and less. So for intuitive or economic or other technical reasons, you may know the partial derivative signs. And that's the beautiful thing. I haven't assumed functional forms, but I have information about these partial derivatives, so I can say something about this, right? How should irrigation adjust to rainfall optimally? Okay. All right. So this part that we have just done is basically using the implicit function theorem, right? Since the problem is very simple, we don't have to kind of invoke the implicit function theorem, but what we are doing here is replicating it, right? But the reason I brought up this example is to make clear the envelope theorem. Okay, so all right, so the value function can be written this way, right? If I plug in the choice function into my objective function, I get the value function by definition, right? So this is an identity. It's not just a mere equation. For every value of a, this relationship holds. Okay. So again, we have, the moment we stumble upon an identity, we can merrily differentiate the two sides and claim that they're equal, and that will be a true claim. So let's do that. So v prime of a equals, it has two terms like this, right? Again, there's a direct and indirect effect. When the parameter a changes, even if x is not adjusted, it directly impacts the value function. That's coming from this part. But the change in the parameter a also changes the choice function, and through that route, it also ends up changing the value of the function. So you have these two terms. Now, I have calculated x prime a, and I can plug that back here, and I can, write down this expression entirely in terms of the primitive function, but I don't need to do that. What is the value of fx at the optimum? This is del f del x. What is the value of this? It's 0. It's x. If x is being chosen optimally, then the first order condition says that the marginal product of irrigation has to be 0. That's where you have hit the optimum amount of irrigation. So fx is 0. So the first term basically disappears, goes up in smoke. It's not there. Right? Its value is 0. So we are left with the second term. So that's what we derive. Okay. Now, this is a simple unconstrained problem. So in other words, what this is saying is that the slope of the value function is nothing but the slope of the objective function itself with respect to that parameter. Yeah. Let me pitch this intuitively. Okay. We are saying if there's a slight increase in rainfall, how will it affect crop yields? Okay. In principle, the answer to that question has two components. If the farmer did not adjust the irrigation water at all, just by virtue of that extra rainfall, there will be some change in crop yields. That's the direct effect of the rainfall change, right? You hold fixed the irrigation level, irrigation intensity, and calculate how much that extra rainfall will directly affect crop yields, right? That's the direct effect of changes in rainfall. But you also know as an economist that you'll always have to take into account people's behavior, and any kind of change from the outside leads to adjustments in behavior. So if there's more rainfall this year, the farmer will adjust his irrigation level. Okay, so in principle, there's a second indirect effect of the rainfall change, that the rainfall change induces some change in irrigation level, and that change in irrigation also has an impact on crop yields. So that's the indirect effect. So your first instinct is to say that, well, I will calculate the direct effect of rainfall. I will then look at the farmer's behavior, how much the behavior will change. By measuring that, I'll calculate the indirect effect and I'll add up these two effects. And that'll be my final answer. Okay. The envelope theorem points out that, look, if we're talking for very small changes, and this won't apply to large changes, right? We're looking at derivatives. So if rainfall increases just slightly, yes, the farmer will tend to adjust his irrigation level. But what was the original irrigation level? Irrigation was taken to a point where its marginal product was 0, right? That slight changes in irrigation in one direction or the other didn't have any impact on crop yields. That is the optimality condition, right? So even if the farmer adjusts his irrigation a little bit, it will have no impact through the first derivative, at least, or a first order effect, as we call it, on crop yields, because already the first order effect on crop yields was 0. That's this fx was 0, so that's why this is disappearing, right? So the bottom line is that the envelope theorem tells us that when we're looking for impact of small changes in parameters, we only have to worry about the direct effects. The indirect effects we can forget about. That's the crux of the envelope theorem. Right? Now, in this simple example, of course, it's much easier to see. That's why I talked about the simple example. The more general, in full glory, what they here, slope of the value function is only equal to the slope of the objective function, because we don't have a constraint function. In the problem, we didn't even have a constraint, right? In a more general problem, we'll have a constraint function. We have multiple constraint functions and so on. And so then the extension of this simple thing that we derived is that the slope of the value function is not just slope of objective function, but in general problems, it's the slope of the Lagrangian function. Questions?
Excuse me, sir.
Yeah.
Sir, I had one question. In the third point, when we're stating that the first order condition has identity, aren't we essentially differentiating the value function only?
Over here.
No, sir, in the third step. First order condition. Yes, sir. So when we insert the choice function, it becomes the value function itself, right? So how is this any different from us differentiating the value function?
No, this is okay. This is the value function is f of x, right? This function, if you look closely, is not the f function. It's the first derivative of the x function, which is a different function. So that's why this is not a value function, what you have on the left-hand side. If the subscript x wasn't there, it would be the value function. But the subscript x is sitting there. That means this is del f of del x.
All right, sir. Okay.
All right. Any other questions? I know at this point it's a bit abstract, so you have to wrap your head around it. We'll see illustrations.
So,
Yeah.
so why did we assume fxx to be negative?
Two reasons. First of all, in this simple problem, right, we are doing comparative statics to the true optimum. Yes. The true optimum has to satisfy the first order condition that the first derivative of the function is equal to 0. It also has to satisfy the second order condition that it won't be a true optimum unless the second derivative is negative, right? So just that itself tells us that, at the optimum point, at the relevant point, the second derivative must be negative, right? So it's coming from conditions of optimality. Whereas fxa could be, in principle, it could be positive, could be negative, but if you want to assign a sign to it, that sign will be basically an assumption. It will come from our knowledge of the problem that we are talking about, right? So in general, when we are doing comparative statics, we derive an expression and we try to guess, whether it will be positive, negative. Can we say something about its magnitude or value? Part of putting a sign on our comparative statics expression, part of that comes from second order conditions. Second order conditions often provide an input about possible signs. Some components of the expression become positive or negative from second order conditions. Some others have to be based on assumptions. Okay.
Okay, sir. Thank you.
So,
Sir?
Yes.
Sir, you said that the slope of Lagrangian function is actually equal to the slope of value function. How
Right.
come that's true?
Well, in this simple problem, I just proved it. In this simple problem, the Lagrangian is basically f function. There's no constraint, so there's nothing to attach to it, right? So the statement of the envelope theorem applied to this simple problem would say that slope of value function equals slope of Lagrangian which in this case is slope of f. So I have proved the envelope theorem for this very simple problem, right? That's the proof I discussed. Now, if your question is, in general, why is it true? Well, I haven't given you a proof, right? That I will confess to. But the proof will run along similar lines. Yes. The proof will probably be covered in maths, right? So many of these mathematical things I'll have to use, but I can't prove them in full generality because then this will become a maths course, right? I mean, we don't have the time for that. But I'm still trying to give you some hint of the logic, some grounding in intuition. So that's why I gave you the proof for the simple case of unconstrained optimization of a single variable. And then I will rely on a goodwill to believe me that the more general form of what we just proved for the simple problem is this, and it is valid. Okay, so if you challenge me, prove it for the most general case, prove the envelope theorem, I will take a rain check on that. Watch the maths course. They'll probably prove it there.
Also, sir, you said that envelope theorem says indirect effects can be ignored.
That's right.
Right. So is it an implication of the theorem, or the theorem itself says this?
It's an interpretation of the theorem. Right? The theorem is all in notation and math, so I'm trying to give you an interpretation. So yeah, it's an interpretation. What does it mean? Yeah, I mean, if you're all happy to be just mathematicians and not worry about trying to understand the maths in other ways, then I don't have to talk about direct, indirect effects. Just look at it, right? But we want to sort of absorb what the meaning is, right? And that's why it's an interpretation of the theorem. In the simple case, you can see, right? That's why I also told you the story about farmers, about all of that, so that it takes hopefully some root in your brain. Yeah, that, oh, what does it mean? Indirect effects can be involved. What does that mean? Well, think about the story about farmers applying irrigation water. How does that respond to rainfall, etc., etc., etc. Yeah.
This makes sense only if there is small changes
Yeah.
like at the point of optimal value, right?
Yeah.
Otherwise, if there are, say, larger changes such that we cannot put fx equals to 0, then it won't make sense.
It wouldn't, but say, again, let me talk very generally. Suppose you have a model, a problem you're analyzing or understanding, and you calculate local effects through derivatives like this, exactly, right? You say, okay, suppose in a problem you find that every time a parameter goes up by a small amount, the endogenous variable also goes up. So there's a monotonic relationship, right? Locally, right? Now, if the local derivative is always positive, if it's all monotonic, then that also extends globally, right? If irrigation always increases slightly when rainfall increases slightly, then you can recursively apply that logic, right? That for 1 centimeter extra rainfall, there will be more irrigation. For another centimeter, even more irrigation, etc. So for a huge amount of extra rainfall, there has to be more irrigation. The problem will arise that when the derivative is positive in some places, negative in some places, then you won't be able to tell for large changes what will happen, right? So it's not true that there's absolutely no connection between local effects, small effects versus large effects.
All right, thank you, sir.
Yeah. Okay, so in the
so one question.
Right, go ahead.
So when does value function becomes identity function?
When does value function become identity function? You talking of this? That's a very broad question, right? I mean, what do you mean? Okay, here's one answer. If I plug in the choice function into the objective function, then it becomes a value function as an identity. That is always true in any problem. That's the definition of the value. One way to define a value function. That find the choice function, the optimum choices, plug it into the function that you're optimizing. That is the definition of a value function. So it's an identity from there. Okay, so in the consumer's problem, let's return to it. Maximize utility, subject to budget constraints, etc., etc. So that problem has a choice function. That's our demand functions. We'll call them Marshallian demand functions because very soon we'll talk about another kind of demand function, the Hicksian demand function, which is somewhat different. So let's call them Marshallian demand functions. And as I said a moment ago, this is the indirect utility function. The direct utility function, the original utility function, which was being maximized, was a function of quantities. Once you plug in your demand functions, you can express utility as a function of prices and income, and that's your indirect utility functions. And these are the kind of comparative statics questions we are interested in, right? Okay, so let me just talk about, just take a moment, since everything was quite abstract, let's apply it to the consumer's problem, and then I'll stop. So some properties of the indirect utility function. What are properties in our consumer's problem? Remember, the indirect utility function is a value function here, right? It's a instance of a value function. So here are some properties. Well, first of all, it'll be a continuous function, right? Let me not dwell on that because the whole problem involves continuous things and well-behaved things. Homogeneous of degree 0, the indirect utility function. What is a homogeneous function? Everybody knows what a homogeneous function is?
Yes, sir.
Right. If I multiply all the arguments of a function by lambda, and the value of the function goes up by lambda to the power k, then it's a homogeneous function of degree k, right? So homogeneous of degree 0, which means that if you, for example, double all prices and income, then each quantity, the quantity demanded of each good will go up by 2 to the power 0, which is 1. So basically it won't change. So homogeneous of degree 0 essentially boils down to saying, if you double prices as well as consumers' incomes, consumers' choices will be unaffected, right? That is, why is that? That's because the set of choices, if you draw, the budget line does not move, right? If you double prices as well as incomes. As a consumer, you face the same set of choices, right? And so your optimum will not change. Strictly increasing in income. If income increases, then the budget set expands. So your optimal utility cannot go down, it can only go up. Because after all, whatever you were buying before, you can still afford it, and you can buy some more stuff and add to that. Similarly, decreasing in prices, right? So all of these you can formally prove, but logic is so simple that I can just state it in words. When the price of one good falls, the budget set expands, right? It moves out. The budget line moves outward. And as a result, the consumer just has access to more choices. The set of choices is larger. And so utility has to be higher. Quasi-convex, I'll leave that to you. You can look at it from the book. Here's a result. Let me talk about this because it's an application of the envelope theorem. Roy's identity. What is this saying? This is saying that if I knew the indirect utility function, I can back out the demand functions from that. Right? Somebody has given me partial information for a consumer, hasn't told me what the demand functions are, but has helpfully supplied the indirect utility function. I don't need to, badger this guy for more information. I can calculate my demand functions from my indirect utility functions. How? This ratio of partial derivatives, okay? Del V del Pi, del V del Y, right? With income in the denominator with respect to prices in the numerator, with a minus sign in front. Why is that? Here's the proof. Here's our Lagrangian function of the problem, right? The envelope theorem tells us that these partial derivatives of the indirect utility function, which is this problem's value function, they're just partial derivatives of the Lagrangian, right? So if I differentiate the Lagrangian here with respect to pi, what do I get? Pi only enters here in the second linear part, right? So I'll get a minus lambda xi when I'm differentiating here. And if I differentiate with respect to y income, I just get the lambda coming from here, right? So now if I take the ratios of these two, the lambdas cancel out and I'm left with minus xi. And that's what gives us Roy's identity, right? It's a straightforward two-liner application of the envelope theorem. Yes. Now, you might ask, why do I care about Roy's identity? Okay.
So?
Yes, just one second. All of these are leading up to general theoretical questions. So let me just state it and then we'll do it in tomorrow's lecture. That this sort of theory, what are the testable implications of this theory, right? A theory is useless if it doesn't predict something which can be rejected by data in principle, right? And then when it's not rejected, we have faith in the theory, right? A theory has to be falsifiable, in the words of philosopher Karl Popper. So when we are building up a theory, we want to know that does this theory tell us anything which has bite, right? Does the theory, for example, predict the law of demand? That if the price of a good rises, people will buy less of it, right? If that was a prediction of the theory that we could derive logically, then we could all try and collect data and see whether that is always happening, right? And if we see that always happening, we will have faith in the theory. So theoretically, the question is, what are the testable implications? How do consumers respond to price changes, income changes, etc., and so on? So that's the sort of destination. That's going to be the final station. That's where we want to arrive. So all of these things like Roy's identity, etc., is our intermediate steps in that direction. Yes, question.
So we have a class, right?
Yes, I'm done.
Hello, sir. Bhavna this side.
Yes.
One of the TA.
Hi, Bhavna.
Sir, I wanted to talk to you. So let the children leave the meeting and then maybe we can talk if you're free.
Sure.
Okay,
so I'll end this meeting and then, Bhavna, I'll send you a link.
Okay,
right,
okay, sir.
In 5-10 minutes.
Okay, sir.
So just a general question.
Yeah.
So are we supposed to know the proofs of these identities and the theorems we talked about in today's class?
You don't have to memorize these proofs, right? I will never ask you, oh, prove Roy's identity, this, that. But you need to understand the logic, how things are done. So in some problem that you're asked to solve, some of the logic or the techniques that we're talking about may come into play, right? So don't ignore it altogether, but don't memorize it either.
Yes, thank you, sir.
Okay, guys. So I'll end it here. I'll take questions if you have, during the session at 1:30.
One small clarification.
Yes.
Are teachers going to post videos on Canvas as well? The tute video.
I mean, I have been posting all the videos. I mean, yesterday's lecture has not yet been posted, but I will post it probably this evening, right? So
I am asking for the tute videos.
For the tutes. We haven't planned to do that. Yes. There should be some incentive for you to come to the tutes are much more interactive. So I don't want to. So yeah, no. Okay. But if you guys feel strongly, let me know about that.
Okay. Okay. Thank you.
Yeah. All right, guys, I'll see you in that session if you have questions, right? So we'll, since we are over time, I'll end it here. See you tomorrow.